So you can solve equations, but can you solve inequalities? Well, I'm going to show you how to get everything from a simple inequality solved all the way to a more difficult one like x cubed shown there. We're going to look at 3 different ways that we can break these down to show them, particularly when we have x squared and x cubed. But we're going to start with that basic case of building the inequalities when we're just solving with the degree 1 on the x. So a polynomial inequality question might say something like determine the possible values for x or determine the restrictions for x. And so in this particular case, like every case we're going to look at, we're going to treat the inequality like an equal sign. If that was an equal sign, it's quite an easy equation to solve. But there's one key thing to remember, and that is that if we multiply or we divide by a negative number, if we multiply or divide by a negative number, what it's going to do is it's going to flip the inequality. Now the second example we look at is going to show how that works and why. But for now, we're not going to encounter this, so we're just going to go ahead and we're going to solve it like we normally would with an equal sign. So what we're going to do first is we're going to subtract 4 from both sides. So we get 2x is less than or equal to 8 minus 4, which is 4. And now we can divide by 2. Notice I'm dividing by a positive number, so it's not going to flip the inequality. So we're going to get x is less than or equal to 2. Now a way to visualize that is visualizing it on a number line. And so if I draw a number line here, 0 is right here, 2 is right here. And so anything that is less than or equal to 2 is what x is allowed to be. So the equal part of it is that dot. And then less than or equal to it means it's anywhere to the left of that. In other words, x can be 1, 0, -1, -2, and on and on and on to the left. Now it can't be anything to the right because x is less than or equal to 2. Let's look at the next example. Now the second question says 10 minus 5x is greater than 7. And keep in mind that if we multiply or divide by a negative, it flips the inequality. So I'm going to start by rearranging it like I would an equal sign. I'm going to subtract 10 from the left side to get it to cancel out. Whatever you do to one side, do to the other. So we get negative 5x is greater than negative 3. So now what I'm going to do is I'm going to divide by negative 5. Now, according to the rule right there, we're going to go ahead and have to flip that. And so what it becomes is x is less than, that inequality is flipped, 3 over 5. On a number line, it looks something like this. 0 might be here, 1 might be here, so 3/5 would be somewhere around there. And so if it was less than 3/5, it means it can't exist at 3/5. So we're going to put a little hole at 3/5, and then everything to the left of that, everything less than that, is what x is allowed to be. Not existing at 3/5, but everything less than 3/5. Now, I want you to see another way we could have solved this so that you can see why we actually have to go ahead and flip the inequality. Because the other thing I could have done, instead of 10 minus 5x and subtracting 10 from both sides, what I could have done when I had that original inequality, I could have brought the 5x to the right. And so if I were to add that to both sides, what I would get is I would get 10 is greater than 7 plus 5x. Now I would subtract 7 from both sides, and I get 3 is greater than 5x. And now if I divide by 5, I get x is less than 3 over 5. So the same answer as this one, but you'll notice we didn't flip the inequality because we did not divide by a negative in the second case. And so it's important to note that you can write it both of those ways. They both mean the same thing. They both mean that x is less than 3 over 5. But what about higher order inequalities? Well, if you have something like x squared minus 5x plus 4, we would normally treat that if it had an equal sign by factoring it first. And we're going to do exactly the same thing here. We're going to go ahead and we're going to say, well, what are two numbers that add to negative 5 and multiply to 4? Well, those two numbers are negative 1 and negative 4. And so because it's a simple trinomial, I can just go ahead and factor that right away. X minus 1 times x minus 4, and that is greater than 0. Now here is where students start getting confused because they say, okay, that's all well and good, but what do you do with two factors? Well, let's consider a few cases. Case number 1. Case number 1 says that we could have a positive times a positive. That would be bigger than 0. Case number 2 says that I could have a negative times a negative, and that would be bigger than 0. But if I had a negative times a positive or a positive times a negative, that would not be bigger than 0. In other words, we want to find out when x minus 1 is bigger than 0 and when x minus 4 is bigger than 0. That's case 1, when both factors are bigger than 0 in order to multiply together to be greater than 0. And case number 2 is when they are both negative, so both factors are less than 0. So x minus 1 is less than 0 and x minus 4 is less than 0. They both have to be true. It's a both and because they both need to be positive or they both need to be negative. So looking at case 1, if we were to solve this, we get x is greater than 1 and x is greater than 4 because I'm just adding 4 to both sides and adding 1 to both sides. And so I don't need to divide by any negatives, so no sign of this flips. Now keep in mind it's an and. So we go to our number line, and when we look at our number line, what we see that 1 is here and 4 is over here. Now if it's greater than 4, what that means is it's like this, from 4 on to the right. And if it's greater than 1, it means it's from 1 on to the right. And so because they both have to be true, they both have to be positive, the only way for both to be positive is where those two lines are overlapping on the number line. In other words, the condition here becomes that x has to be greater than 4, everywhere in here where the lines are overlapping. So that's the first case. That's the condition on the first case. Now we can look at the condition on the second case. This means that x is less than 1 and x is less than 4. Again, going to our number line, if we have 1 right here and we have 4 right here, well, less than 1 is from here. No, it's a hole. Make sure we draw it as a hole. So it's from there on over. And less than 4 is from there on over. So where is it overlapping? Where is it both x is less than 1 and less than 4? Well, it's going to be in the overlapping segment. So that means here that x has to be less than 1. So in other words, your x value has to be greater than 4 or less than 1. If that isn't quite doing it for you, let me show you another way to see it. And then I think this will be really helpful and more visual for those visual learners. So a second way to look at this third example is graphically. What I'm going to do is I'm going to treat this as I would a normal function. So I factored it as I normally would. And then what I'm going to do is I'm going to set my x minus 1 equal to 0. So we're thinking about this for now as an equal sign. So we're just ignoring the greater than sign for now and thinking about it as an equal sign. And I would get x equals 1. And my x minus 4, if that was equal to 0, I'd get x equals 4. And so what I would do is I would go ahead and plot my x values at 1 and at 4. Those are my x-intercepts. And we also know that the leading coefficient here is 1, which means that this is a parabola that opens up. The coefficient on the x squared term, if it's positive, opens up. If it's negative, it opens down. And so without any more needed detail, we know that our parabola is going to look something like this. We don't know what the vertex is. We don't know what the y-intercept is. We don't care about that. Because all we care about is that this equation is greater than 0. Well, if that equation is represented by a parabola, where is that parabola greater than 0? The parabola is greater than 0 everywhere up here. In other words, what we can see is that x cannot be between 1 and 4. So the only allowable values for x are from 1 and below or from 4 and above. So we'd say that x has to be less than 1 or x has to be greater than 4. And that's the same answer that we get by doing it the other way. All right, ready for a degree 3? Let's do it. Before you try to tackle this question, it's very important that you know how to do synthetic division and long division of polynomials for that matter. So if you check out those videos, if you're not comfortable with that, I have those listed in the description. And once you've got that, come on back to this and try to give this a go. So x cubed minus 2x squared minus 5x plus 6. Just like we did for the quadratic case, we want to factor this first. Well, the way to factor this is we want to figure out what the possible rational roots are of this particular cubic function. Well, the possible rational roots for a cubic function with a leading coefficient of 1 are always the common factors of 6 of that last term. And so the possible rational roots here can be plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. Now we're going to start by just trying the most basic one, which is 1, and see if that works. So I'm going to take my 1 and I'm going to synthetically divide that into my x cubed followed by my x squared term. And so with synthetic division, we write these out as 1, negative 2, negative 5, and 6. And so what I do is I go ahead and I add that to 0, because that first column, that's just a placeholder, it's a 0 there, and we get 1. And now what we do is we multiply the 1 times 1 and we get 1 again, and we write that in the next column, and we add it to the number above it, so we get negative 1. Now the 1 out front, again, we multiply by that bottom number, negative 1, and we get negative 1. Add to the number above it, we get negative 6. 1 times negative 6, I write the negative 6 there, and I get a remainder of 0. And if that last term after synthetic division is 0, it means we have no remainder, and we've been able to factor that. So what this gives us is it gives us that this is x squared minus x minus 6. Now, that's the results after we divide by this other root. And the root was 1, which means the factor is x minus 1. And so in its complete totality, we would write this as x minus 1 times x squared minus x minus 6 is less than 0. Now we can also factor that, the quadratic part of that, two numbers that add to negative 1 multiply to negative 6. Those two numbers are negative 3 and 2. And so what I can do is I can finally write this out as x minus 1 times x minus 3 times x plus 2. And you'll notice that all of those are rational roots, and all of those are one of those possible rational roots that I listed originally. And so that comes down to the rational root theorem. And so you'll want to use that to find those roots, particularly if it's not an obvious one at the beginning. Here, 1 worked out really nicely, so it's really good. So now we get this factored form, but it's not quite like the case for the quadratic, because we actually have several more cases. And if you were to try to list these cases, we could say case 1 is when you have a positive, negative, and then a positive. So if the first factor was positive, next one was negative, next one was positive, that was less than 0. Case 2 would be when you have a negative, positive, positive. So one of them is negative. Case 3 is when you have a positive, positive, negative. And you can just see how many cases we can eventually come up with. We continue that out. Case 4. Case 4 would be a situation where the first one would be maybe negative, the next one would be negative, and the final one would be negative. And so if that was the case, that would also be less than 0. And so I think that's pretty much all the cases we can come up with, but we'd have to solve each of those 4 cases and solve the inequalities in those cases, and we could totally do that. But what I want to suggest to you is 2 other ways to do that as well that I'm going to look at in more detail that are actually more effective and more helpful, particularly when you get into cubic or even larger degree functions. So let's have a look at those. The first one is graphically. So graphically, how do we go about solving this? Well, what we can do is we can graph the function x cubed minus 2x squared minus 5x plus 6. And so we know that these are the factors which give me roots of 1, 3, and negative 2. So what I'm going to do is I'm going to go ahead, I'm not graphing this super accurately, but I'm going to 1, an x value of 1, an x value of 3, and an x value of negative 2. And so I'm going to go ahead and plot those points. This is 1, this is at 3, and then negative 2. Now the other thing I can do when I'm graphing a cubic is I'm looking at the leading coefficient. The leading coefficient is degree 3, and it has a coefficient that is a positive leading coefficient. So what that means in terms of what quadrant it starts and ends in, it means it's going to start in quadrant 3 and it's going to end in quadrant 1. And so by looking at that leading coefficient and by looking at the degree of this, I knew it was three roots, and so that meant it was degree 3. That's how I'm able to conclude quadrant 3 to quadrant 1. So what I have is I have a function that comes up like so. Again, I'm not concerned about how high up it goes or anything like that, because we're just asking ourselves, is it greater than or less than 0? Just like we did for the quadratic case. So it's doing something like this, and then it's coming back up like so. We want to know where it's less than 0. And so where it's less than 0, it's less than 0 everywhere down here. What are those intervals where that's the case? Well, it's where x is less than -2, not equal to, so we should say less than -2, okay? And it's where x is between 1 and 3. So -2, and then from 1 to 3. So what we can say is that x is less than -2, or x is between, we could write this as +1, so it's greater than +1, or less than 3. And so that is our solution. Based on our cubic function graph, we can see that it's only the part that's below the x-axis where that function exists that gives us those restrictions or those possible values for x. The third way to look at this is to look at an analysis chart, but we first want to identify what the roots are. If the factor is x minus 1, it has a root of 1. If it's x minus 3, it has a root of 3. And if it's x plus 2, it has a root of -2. And so what we do is we build intervals from all of those numbers between them, and then at all of those numbers as well. So we start with the interval that goes from -infinity all the way up to the smallest number, then is at that smallest number, then goes from that smallest number up to the next smallest number, then is at that next number, and then goes from 1 now to 3, and finally at 3, and then greater than 3. And what we do is we analyze each point along that by looking at what would happen if I substituted a number in that was within each of those intervals. So let's go ahead and look at the sign overall of f of x. So f of x is my entire function. So if x is less than -2, what we're doing is we're substituting into that factored form, we're substituting in a number that's less than -2. An easy one to choose would be -3. So if I put -3 into all of those, what we would end up getting is we end up getting the first term, that x minus 1, -3 minus 1 would be a negative. The next term would also be a negative, and the next term again would be a negative. So overall, all three of those terms multiplied together would give me a negative, because an odd number of negatives is negative. Now, if I substituted -2 in for the next interval there, at -2, you can clearly see that third factor would end up being 0. And so 0 times anything is 0. So now we choose something between -2 and 1. 0 is the easiest one to choose there. And if I sub that in, you get a negative times a negative times a positive. And so what that means is that between -2 and 1, overall, that would multiply to give you a positive value. Two negatives always make it positive. So now we look at 1. If I sub 1 in for each of those values, we get 0 again, because 1 minus 1, the first factor, would become 0. Now we choose something between 1 and 3. If I choose 2, I can see that what ends up happening there is I end up getting the first term positive, the next term is negative, and the final term is positive, meaning overall, in that interval, we have a negative overall value. We check the next thing, which is 3, and the middle term ends up being 0. And so that's really the basis of this. Every single time we are at one of the factors, it ends up being 0. And now we check a value when x is greater than 3. So let's choose 4. And so we end up getting, as far as the signs for that, would be a sign of positive, a sign of positive, and a sign of positive again. And so that would be positive when x is greater than 3. And so remember, we're asked when all of this is less than 0. So we look at our analysis chart and we say, well, when it's less than 0 is when it's negative. And so that's when x is less than -2 and when x is between 1 and 3. And those are the solutions for x. So we ultimately have 3 ways to analyze things. The first way is to look at all the different cases and then put those together on a number line. The second way is we can look at a graph, and after graphing it, we can put it all together. The third way is to build an analysis chart. And really, you can choose which is best for you, but you may have situations where you're asked to do one thing instead of another. So it's good to have all 3 of those possibilities as ways to do it. For all about how to graph a higher order polynomial function, check out the video on the left. If you want a video about how to solve trig equations, check out the video on the right. Thanks so much for watching. I hope that was helpful.